Okay, so we are doing lesson 4, Coulomb's law, and this is where we're going to get into talking about the electrostatic force. This is what we've been building up to. So let's start with the first do not question. What is the equation for counting charges? Again, we got Q equals NE, where Q is the charge. N is the number of the elementary particles, and E is the constant, the 1.6 times 10 to the negative 19 coulombs. So question 2. A metal sphere has a net negative charge of 1.1 times 10 to the negative 6 coulombs. Approximately how many more electrons than protons are there on the sphere? So I just want to point out this 10 to the negative 6 is, if you look at your reference sheet, 10 to the negative 6 is also, you can see this mu, or it's equal to micro. So you're often going to hear this called micro coulombs. Alright, so it's just, in this problem, they gave us the Q, the charge. We know that E is the constant. We're using a negative value here because we're talking about electrons. How many more electrons than protons? And we want to solve for N. So we have this equation, Q equals NE. Solving for N, we're going to have N equals Q over E. It's pretty straightforward from here. You're going to see coulombs are going to cancel out. And you have this really big number. So it is a lot of electrons. And it's not even close to being 1 coulomb. So let's talk about it. Electrostatic force describes the force of attraction or repulsion on an object due to a charge. What factors do you think influence the strength or force of the attraction? So there are two things that can influence how much force between electric charges. Can you guess what they are? We have two. So we is directly proportional to the charge of the object. So if you increase Q, you're going to have more force. If you decrease Q, you're going to have less force. And it's inversely proportional to the distance. So the closer they are, the much more force. So if R here, normally we reserve that for radius, but in these examples, R is always going to be the distance. So as these get closer, R gets smaller, and it's in the denominator. So you can see your force will go up. And the same is if the objects are much further apart, then the force will go down. So this was named after Coulomb, this French general who dedicated his life to physics after a war and studied charges. So we have the electric force, and it's equal to this K, Q1, Q2 over R squared. K is a constant. It's on your sheet, reference sheet, so you don't have to memorize that. 8.99 times 10 to the 9th newtons meters squared over coulomb squared. And you get Q1, Q2 all over R. So, yeah. So this is basically Coulomb's law. And the force from one object is equal and opposite to the force on the other object. What does that remind you of? Indeed, Newton's third law. The electrostatic force on one object is equal to the electrostatic force on the second object. So if we remember, we said opposites attract. So here we have a positive and a negative, and their force is going to be directed towards each other. And here we have a negative and a negative, and they're going to repel. So when you do these equations, because your Q, here I'm going to write it here, Fe equals K Q1 times Q2 over R squared. So if your Q's are of the same sign, like if you have two positives, you're going to have a positive answer. Or if you have two negatives, a negative times a negative, you get a positive answer. So if your Fe is positive, then you know that they're going to repel each other. Conversely of that, if you have a positive Q and a negative Q, then they're opposite, then your answer is going to have a negative. So if you have a negative Fe, then you know that they're attracting towards each other. So you may have noticed that this looks exactly like the equation for gravity, and it's kind of neat how nature works like that. And if you look at, well, we're not going to get to that now, but the electrostatic force is much stronger than gravity. So when we graph the distance versus force, you're going to see it follows this curve. Sorry, I don't know what's up with this extra box here, but as you get much further, if you have a big R, you have very little force, and if you have a very little R, you have a very big force. But in between, you kind of follow this curve. It's called an inverse square law. So I'm gonna move to another. I guess I can do it right here. Let's find the force of attraction between two balloons. So I got Q1 is equal to 3.5 times 10 to the negative 8 coulombs, and I got Q2 is equal to negative 2.9 times 10 to the negative 8 coulombs. And they are separated by 0.65 meters. Wait, did I work this one? Oh, I did. I don't have to write it all out. I just have to look over it. So I got my equation, plug it all in. So here's the thing. A lot of people are going to forget this square. And I definitely suggest you do it in your calculator. Make sure you get the same answer, which is 2.6 times 10 to the negative 5th newtons. And they're attractive. So I could have left it as negative 2.6, but since I wrote attractive, we know they're attractive. So you're going to get some problems like this on the regions. We're going to say, well, what happens if, and like in this case, if the charge of one of them is doubled and the distance separating the objects is doubled? What's the new force? So you don't even need to know, you don't have to do math. You just have to look at the equation. So if you double this guy, you double your R, you're going to get 2 over 2 squared, which is also 1/2. So now you have half the force. Because here's the thing, 2 is inside this parentheses here, so that's why it's 2 squared and becomes 4. You pull these guys out, you get 1/2. It's 1/2 as strong. Again, I'm going to skip this part. I'm going to save this for electric fields. And so this is what was going on with the Van de Graaff generator. The Van de Graaff generator was ripping electrons off, and actually this says it becomes a positive sphere. And all these excess electrons come over here, and you get a potential difference between these two. And these like charges, they don't want to be near each other, so they're pushing away. So this is why her hair is all flying out, because the electrostatic force is pushing them apart. Alright, so I'm going to switch over to this guy. Alright, let's do some practice problems. The electric force between two balloons that are charged equally but opposite. So I know I got Q1 is equal to 6.0 times 10 to the negative 7 coulombs, and Q2 is negative 6.0 times 10 to the negative 7 coulombs. And I know I've got R is 0.5 meters, and the equation KQ1 Q2 over R squared. I guess I can throw my K here. What is that? 8.99 times 10 to the ninth newtons meter squared over Coulomb squared. So substitute in 8.99 times 10 to the ninth newtons meter squared over Coulomb squared. I like to put these in parentheses just because for me it helps tidy things up. And positive 6 times 10 to the negative 7 coulombs. All of this over 0.50 meters squared. And I can already see that my Coulomb squared is going to cancel out, my meters squared are going to cancel out, and I'm going to be left with newtons. So please put this in your calculator, check, because this is the hard part. It's just making sure it works with your calculator. I get negative 0.130 newtons, or you can just say 0.130 newtons attracted. Because they're oppositely charged, you know they're going to pull towards each other. It's a good check. So now I've got a point charge, 3.0 times 10 to the negative 7 coulombs. And they gave me distance, so I'm going to skip over that. I want to know Q2. I like to have these together. Plus 4 times 10. So these are just two positive. Negative 7 coulombs. Now I'm going to go back. They are 2.0 times 10 to the negative 2 meters. And they want to know that Fe is electrostatic force. So once again, Fe equals K Q1 Q2 over R squared. Fe is equal to 8.99 times 10 to the 9th newtons meters squared over Coulomb squared. 3.0 times 10 to the negative 7 coulombs times 4.0 times 10 to the negative 7 coulombs. All of that over 2.0 times 10 to the negative 2 meters. So in this case, it's definitely important that you put parentheses in the denominator and you don't forget the square root, because a lot of people are going to do that. You do that math, check your calculator, and I got 2.7 newtons. And I know they're going away from each other. I didn't ask for that, it's just asking for the magnitude here. But I can just say repulsive. Let's do number 3. So I have a balloon with an excess of 50 electrons and a balloon B with an excess of 300 electrons. Find the electrostatic force between these two balloons and when they are separated by a distance of 10 centimeters. So here you go. You have to ask yourself, what did they actually give me? Did they give me Q? Actually, no. They gave me the number of electrons. So we got N. And I got N1 is 50E, and I got N2 is 300E. So I'm going to have to use that equation. Q equals NE. So, handwriting's bad. 50 times 1.6 times 10 to the negative 19 coulombs. And Q2 is equal to 300 times 1.6 times 10 to the negative 19 coulombs. Q1 is, check. I got 8 times 10 to the negative 18 coulombs, and Q2 is equal to 4.8 times 10 to the negative 17 coulombs. Now I can do my electrostatic force problem. 8.99 times 10 to the 9th newtons meter squared over coulombs. Wait, is that right? Yeah. Wait. Spacing. Yeah. Times my Q1, which was 8 times 10 to the negative 18 coulombs. 4.8 times 10 to the negative 17 coulombs. That's my Q2. All of that over, what did they give us? R was 10 centimeters, which is actually 0.1 meter. 0.1 meters, and all that squared. You might want to check my work, but I got 3.45 times 10 to the negative 22 newtons. And these are two negatively charged, so it's going to repel. Alright, so this is a very interesting problem. Last problem. Object A, which has a mass of 0.05 kilograms and a charge of 1 microcoulomb, is resting on a surface. A student wishes to lift object A with object B, which has a charge of 3.25 microcoulombs. How close must object B be to object A to lift it? So basically, I got this object on the ground, and I know it has a mass of 0.05 kilograms, and it is a... Wait, am I giving that wrong? Oh, no, that's right. And it's a +1 microcoulomb charge. So, and it wants to lift it using the attractive electric force with this guy is 3.25 microcoulombs. So basically the two forces acting on this guy is the force of gravity and the electric force. So the only way you can lift this is if the electric force equals the gravitational force. So we remember that mass times gravity is the gravitational force. And we learn this new equation for the electric force. And they want me to solve for how close. So R. So I want to solve for R. Oh, actually, I'll just do it over here. I'm going to write it over here in case you want to just keep looking at that. So I got K, Q1, Q2 over R squared equals mass times gravity. If I multiply both sides by R squared, they will cancel out on that side. Just spelling this out for people having trouble with algebra. And then divide by mg on both sides, and those cancel out. And then I finally get my equation. R squared equals K Q1 Q2 over mg. So I will substitute in 8.99 times 10 to the 9th newtons meter squared over coulomb squared times my again, you see this micro, it's equal to 1 times 10 to the negative 6. So I've got 1 times 10 to the negative 6 coulombs and a negative 3.25 times 10 to the negative 6 coulombs. all of that over mass times gravity, which in this case 0.05 kilograms times 9.81 meters per second squared. And actually, I'm just gonna, well, I can leave that there. I'm gonna go ahead and take the square root of all of this. So make sure all that is in you. I mean, you could square root your other answer, but I just went ahead and did this. And you can check my math, but I got 0.244 meters. So when this object up here is 0.244 meters, it's close enough to have electric force, attractive force that overpowers gravity and is able to lift it up. So thank you for going through this lesson with me, and I